All right, we are going to make sure that everything is up and running. Gonna make sure my stream is actually running, which it might not be. All right, let's see. Where are we sending the stream? Twitch, Facebook, Picardo, YouTube, Stream Now, Mixer, and Steam. Nice. All right, I gotta get my chats up and running. Okay, it looks like everything's running. I just want to make sure I have the video on record. So, hello everybody. This is going to be a beginning of a little bit of an experiment. So, what I am looking to do is I'm looking to see if I can create some little tool which will allow me to record video footage off of a 3DS. So, I've never had a 3DS. I had a long time ago. I had a Nintendo DS Lite, and I mean, it didn't really tickle me all that much. But to be honest, it was like a collectible thing more than I was actually playing it. So I was more interested in just owning one than actually playing games on it. But ever since we kind of ramped up activities with Retroactive Gamers when we do recordings, I actually figured it might be an interesting idea to do a recording of Luigi's Mansion. And lo and behold, not all Luigi's Mansions are available on hardware that can be captured, at least not in an easy way. Now, the 3DS has some emulators. It has some stuff to work with, but according to one of the people on my Discord forum, actually, his name is Hyas, and I kind of want to post a couple of his links here, his Twitch at least. It just so happens that the video stream is not very good. The quality, there's some latency problems. It chugs your memory. It chugs your processing power, because essentially what's happening there is your 3DS has to not only play the game, but also run the background application, which dumps the video. I'm not sure if it captures it or if it just reads the existing video storage of the LCD displays, and then it just dumps it onto the controller, which sends it to the computer, and then the computer, with its own software, it kind of decodes the video. So with that in mind, if having a secondary application on this DS, on the 3DS, makes the DS run slower, then that's probably not what I'm looking for. I am looking to just play the game comfortably the way it was made, without, dealing with frame drops and all that fun stuff. So the idea here is, instead of trying to have a piece of homebrew software running on this piece and taken away from its processing power, is to actually intercept the signal that is leaving the 3DS and goes into the two displays, and from that point on we would be able to simply kind of get the data and read it with the controller, and the controller will transfer it onto the computer, where we can assemble it and maybe capture it or preview it or do something about it. Now, I just received this today, which is why I want to make this little introductory video. So I'm kind of excited about it. Never had a 3DS in my life, so this would be an interesting little experience. Didn't come with a power adapter, didn't come with a stylus. So I am still waiting for the power adapter. Can't turn this thing on. They said it's working. They showed pictures that it's working. The power adapter should come in a matter of maybe a few days. I ordered it on pretty much the same day. And if it doesn't work, then I can always return it. Or, I mean, I'd probably return it, 70 bucks. I do have a second one coming, that one I bought for $15, and that one is broken, and I just want to see if I can maybe crack that one open and see if I can fix it, just for the hell of it. If not, then $15 to crack open the 3DS. That's a worth of worth of an investment. So, with this 3DS, there's actually a whole bunch of research that the community has already done on the subject. So, the homework on it has pretty much been prepared. So, what do we have here with this 3DS? We have two displays. So, I'm going to have to be dumping the information from both displays. And we have to have some sort of a way to read that data, which is what I'm going to be using, for which I'm going to be using a microcontroller. And it's got to be a pretty fast one too, considering that the two displays, they run, I think, at 60 megahertz refresh rate, which means that we are going to have to be able to read the data quite quickly. So we're going to need to get ourselves a controller that has the capacity to keep up with these speeds. So we're going to see what sort of hardware I have available and what it is that we can use. Now, let's take a look first of all at the research information that we have available for this little project. So I'm going to quickly switch to my display. Okay. So here we have the wiki for the 3D Brew. We have pretty much the pinout of the both displays. So what are we looking at here? We have the little graphic here. I'm actually gonna open that up in a new tab. Now we're gonna open this image up and zoom in. Okay. So same exact graphic as we have here. I'm gonna zoom in just a little bit. So everything has been labeled, and this right here is actually a capture card that is apparently no longer available. Nobody's making these, or the company that originally made these doesn't make these anymore. So this is technically antique hardware now that you probably find for about $200 according to Highest. So yeah, I want to record 3DS footage. I don't want to record it $200 worth for 3DS footage. So plus this is actually kind of it might even make for an interesting experiment. Now I have no idea what this thing is. Well, judging by the amount of pinouts and judging by the fact that they're not using nearly enough pinouts pins from this controller, tells me that this is some sort of an evaluation board, maybe like a little project board, which means that this is just kind of generic piece of hardware that you can get off the market. Now it says the word blue right there, 4-bit, and I can't read sushi, so we're gonna keep going with this little board here. All the connections are pretty much wired up here. Now let's see, what is this controller actually called? Let's do some research here. It's the Altera Max 2. Okay, can't read upside down. So let me pull up a new guest tab. Thank you very much. Okay, so Altera Max 2. So the Altera Max 2 device handbook, looks like it's an Intel chip. Okay, so a lot of development boards. Device handbook. So what do we have here? How to connect Altera, typographic conversions, function description, logic array blocks. Introduction. Two-dimensional row and column based architecture to implement custom logic. Row and column interconnects provide signal interconnects between the logic array blocks. Okay, so rows and columns. That sounds interesting. That sounds almost like the horizontal and vertical refresh of a display. That's fascinating. Okay, so the Max 2 device I/O pins are fed by I/O elements. Okay. Blah, 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 blah. pins Schmidt triggers input in various single-ended standards, such as 66 megahertz, 32-bit PCI, and okay. Fascinating. Now, this could be possibly the speed of the processor. Maybe. Who knows? Let's see if we can... let's see if we can find some just plain old chart of stats for this. Device family datasheet, revision history, chapter introduction, reference documents, introduction, functional description. I just want to see what sort of hardware we're working with in here. Fast AO Schmidt trigger. Right, okay. So let's take a look at maybe like a store page. Max 2 device handbook, Max 2 FPGAs. Although that, yeah, that's from Intel. Fascinating stuff. Looks like they're actually they're making their own dev board. Something I didn't know about. Development micro kit. Sheesh. $150. That's some stuff. Okay. So I'm gonna shelve this. What I want to take a look here on this particular diagram is their connection setup. So they've labeled all the pins of how you would connect the controller to this board. This is, I believe, half of the bottom side. So this would be underneath the screen. So there's the D-pad right there. So we're looking at it from the left side. All of these pins here are essentially probe points. That's why they have these big old circular pads. This is so that the engineers could essentially debug the information on their screens while they're developing this little gaming console system. So it's kind of nice for them to implement it, because now you can just kind of solder this to all of these representative pads, and you'll be able to get yourself direct connection with the signal, with the video signal to your controller. I'm gonna see if I can do something different though, like for a test, sure, just to figure out if I can even read the information in the first place. Yeah, I can go ahead and just kind of read up, just solder the pins on my controller to these pins on the console as well, and read the information from there, just so I can, you know, lay down the groundwork. Now this chart here is fascinating. This chart actually pretty much does all the work for me. And you see we have pin labels. So what are these pins? Well, we have CN2, CN1, CN2, CN1, CN2, CN1. My guess is that these are channels, or LCD channels, so to speak. So channel 1, channel 2 being screen 1 and screen 2. I'm just kind of going off the top of my head. I don't know if we are going to have to, you know, maybe probe around a little bit and see if maybe there's a second set of these. So what I'm thinking here is that we have, let's say channel 2, R6, R4, R5, R7. This is the red color. Then we have channel 1, B4, B5, B6, B7, which is the blue channel. And then we have green, G, G7, G3, G6, G5, and that gives us the green channel. Now let's see, we have 1, 2, 3, 4 reds, 1, 2, 3, 3 blues, but I'm guessing they're staggered all over the place. There's blue 1, blue 0. So 0, 1, 2, B3, B3, B4, B5, B6, Where's B6? B6 and B7. So if we actually take a look at the labels here, let's see, B1, oh, B0, channel 1. B0, channel 1. B2, channel 1. B3, channel 1. B4, channel 1. B5, channel 1. B6, channel 1. B7, channel 1. B8. Do I have B8? Oh, technically from 0 to 7 you get your 8 bits of information. So this is kind of interesting. So I'm gonna try to make sense of this labeling convention, so to speak. We're gonna copy this. We're gonna open up Paint. Okay, so my logic of this originally was the fact that this is actually the information for both screens. So okay, so I'm just gonna enable my tablet so I can actually draw instead of using my mouse. Okay, so my general understanding is that this is channel 2. So let's say we are going to put something like a label for each channel type. So let's actually count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so we have a total of 12. Oh, that's way too small. Let's do green. Okay. 12. 12 bits. Wow. This. You know what? Let's do this in Krita. Yeah, screw Paint. Paint does not like my tablet. Pen tablet. Okay, so the basic idea here is we have 12 bits for channel 1 and 12 bits for channel 2. Why 12? Well, if you divide 12 by 3, you get 4 bits per channel, red, green, and blue. 4 bits of red, 4 bits of green, 4 bits of blue. Which means, let's see, I'm just going to wait for Krita to load up because I want to take notes of these thoughts. 12 bits, so technically you'll have, when you're thinking about color, red, green, and blue, you have to send that color to the display. And that color, like for example, the brightness of red, the brightness of green, and brightness of blue in conjunction with one another will determine the end color and the end brightness of a pixel. So if you have red, green, blue, your red is at full brightness, your green and blue are at 0 brightness, you get the fully bright red color, the rich red color. You mix red and green and blue in full intensities together, you get the white color. So, okay, we are going to launch a nice little display. Yes, sir. Okay, this will be 1920 by 1080. Okay. All right, so let's load up the thing in here as web. Good. So what I want to do is I kind of want to just make something clear. So let's say screen 1 is going to be green. So we're gonna do channel 1, 2. These are okay. These are red. Let me actually make this visually pleasing for myself. Red, 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 and then we have red, 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 red. Then we have green, 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 and then green, 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 green. So these are actually bits of a parallel port, and I'll cover that in just a moment. Then we have blues, blue, 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 blue. Okay, good. So now if we take a look at this, we have blue channel 1, blue channel 1, blue channel 1, blue channel 1. And then we've got blue channel 1, blue channel 1, which doesn't really make sense to me. Shouldn't it technically be blue channel 2? So the display, if we take a look at the display pinout, the page says that this is the table that shows the test points to get the bit of the corresponding color, red, green, and blue, and the TP to get the clock, vertical sync, and horizontal sync test points. So the basic idea here is we have channel 1, channel 2. The basic idea is that when you're working with a screen, if you want it to refresh really quickly, you have to use a parallel port. And I'll come back to this in just a moment. So when you have a display, let's say we have a display like this. It's a tiny little display. You can either send the data in a serial manner or in a parallel manner. So we have a single wire. Let's say it's the data in wire. So you can send the data in as a single string, so to speak, as a single like flow, not a string. So you'd have something like red 1, red 2, red 3, and then you would send, technically this would be in reverse, by the way, and just to make it a little bit less stressful, let's just do this. So you do red 1, red 2, red 3, green 1, green 2, green 3, technically green 4 if you're dealing with red 4, and green 4 if you're dealing with I believe it would be, if it's 4 bits, then you get 16-bit display. That's the color depth of your display, 16 bits. And then there's blue 1, blue 2, blue 3, blue 4. Okay. So if it's a serial data, you send them like this. However, the problem is you essentially you're never gonna get 60 megahertz per second with this sort of an approach, and the data would look like something like x0x, so something like a hexadecimal value. Say we're gonna do 0x, so f and ff would give you white color. This is the red, green, and blue color. So technically they will be reversed in this case, where since this is just going to be receiving the red color first, green color first, blue color first. So as I said, the problem here is that the data that's going to be coming into the display in the serial manner, that's way too slow. I have serial displays, but I have worked with serial displays, but there's just, you're not going to get like real-time refresh rates, nowhere near 60 frames per second. So this is why instead of doing this serially, you actually use a parallel port. So we're going to get rid of that. We're going to get rid of this. And instead of doing, let's say, a digital in, you can do something like red, green, blue. Okay, so now instead of having sending all the data about the entire color, the entire picture of the display in a single string, in a single stream, I should say, you actually split it into three inputs. So now you're actually receiving like 0x, let's say FF, we're going to work with a white color. So you're only receiving the red color here. You're receiving green color here. And you're receiving blue color here. The main difference is that if you had the original serial input instead of the parallel one, like we have here, how many clock cycles would it actually take for you to get the data in? Well, we have 0. Let's say we're working with a white color, so instead of the hexadecimal value, I'm going to use binary. So we say we're sending first the red color, then the green, then the blue. So you have to send 1 1 1 1, green 1 1 1 1, and screw it. Let's say it's 0 0 1 1 for the for that color, which should be able to should give you it's not going to be, this is not technically the halfway point. So if it's 1 2 3 4 4, then this would give you technically, oh my bad, I'm an idiot. It's a power of 2. What am I doing? Yeah, so if I do something like this, 0 0 0 1, then we would get blue only at half brightness. Okay, so how many clock cycles would it take to actually get this information in? So 1 2 3 4 5 6 7 8 9 10 11 12 clock cycles. So technically, if I were to illustrate this as a clock, and then that, there we go, and finally our final blue. Okay, so a total of 12 clock cycles is how long it would take to send 1 pixel worth of RGB data. However, if you use parallel port, so we're going to once again, instead of using hexadecimal values, so let me just use our binary code. We are basically going to say red 1 1 1 1, green 1 1 1 1, and then blue 0 0 0 1. Okay, so in this case, we're actually only sending the same amount of data, but we're actually sending it in a span of only 4 cycles, 4 clock cycles. Right? So this is the power of parallel port programming. Now, of course, you are going to have to use more pins. So instead of 1 pin here, you have to use 3 pins for red, green, and blue. And depending on your application, you may go with one, you may go with another. If it's a slow refresh display, like for example in my case, if I have a project that uses, say, a display to just show some status information with some numbers that update maybe like once every few seconds, then there's really no point in having a parallel port, and it would be a lot easier to just implement a serial port. You just send, oh, we have an updated value, let's send it to the display, and that's it, we're done. For those applications, serial ports are just fine. With the gaming application, where people expect you to get 60 FPS refresh rates, that is where you have to think about speed. And that is exactly why we don't get 1 red, 1 green, 1 blue input or output from the board and input into the display. We're actually getting 4 per each color, per each display. So realistically, This doesn't even look like that on the actual display board. If I actually put in a second display right here, which is just like another version of this display, it's not the bottom display. So technically in here we get this. We get red channel gets 1, 2, 3, 4 pins. Green channel gets 1, 2, 3, 4 pins. And blue channel gets 1, 2, 3, 4 pins. And Hyas is complaining that I'm making this live stream while he's away doing martial arts. Oh well. Sorry, buddy. It'll be available as a video. So this is where the real parallel port advantage comes into play. Because now check this out. What do these dots basically mean? Well, these dots are actually individual bits of the color. Now, what do we have here? We have red 1, red 2, red 3, red 4. And then we have red 5, 6, 7, and it starts with red 0, so that's your 0 bit. The one thing I am not certain about is whether or not CN1 and CN2 mean display 1 and display 2. So let's assume that these are 4 bits of the individual colors. Let's say this is a 4. Every color gets 4 bits. Maybe. Like, who knows? It could be plausible. It's a Nintendo 3DS. Should it have a high bit depth color, or should it just have something less I forget it skips my mind. If you want to make a 3DS affordable, are you gonna put like a super high fidelity screen on it, or should you settle for something that's gonna do the job and it's gonna be fast? And I'm thinking that I'm pretty sure that these 4 displays, these are actually 2 displays, these 4 bits for each display, mainly because if you have a high bit depth display, you will actually need a lot more pins to drive that display if you want to drive it in a parallel fashion. So what do I mean by that? Let's assume that these 4 colors is for display 1, these 4 colors are for display 2, even though it says R0, R1, 2, 3, 4, 5, 6, 7. Okay, let's say it's one display. So R7, 5, 4, 4, 5, 6, 7. So we're gonna do red, green, blue. That blue looks like a D. Okay, blue. So this is R4, R5, R6, R7. If we look at this as binary, then this is technically, this right here is technically, let's say it's 0, 0, 0, 0. So let's say the red channel is completely black. So what do these zeros mean? Well, this is 4 bits of a 4-bit byte. With a byte being, in this case, a byte is usually 8 bits. In this case, the byte would be 4 bits. I'm pretty sure the word for that is called the length of the word, or the size of the word, if I'm correct. This is an actual term for it. So what does this mean? This is your red color of that particular 1 pixel. How big is the display? How big is the 3DS display? What's the resolution on 3DS display? Let's look this up. So we are going to pull up this. So we're going to do 3DS display resolution. Okay, so we have Nintendo 3DS top screen is 800 by 240. Nintendo 3DS. Okay, so since it's a 3DS, they also kind of provide you with the numbers where it divides it per eye, which kind of makes sense because technically, when you're working with 3D effect, you're actually hiding half the pixels for one eye and for the other eye in order to sell the 3D effect. But what I'm going to do is I'm just going to take this And, oh, can I actually take the entire thing? It's gonna be my little cheat sheet. Okay. As web. So what are we dealing with here? This is the size of our display. This is the red channel of a single pixel. So if there's 800 pixels, we have to receive 800 of these, and we have to do so 60 times per second, if my math is correct. So if this display refreshes at 60 frames per second, that's 60 times this multiplied by this, and that gives you the entire picture. That's a lot of data, man. That's a lot of freaking data. But hey, whatever. We'll see what comes out of it. So what's happening here? If you take a look at binary, let's say we're working with regular binary. So we say it's 0, 1, 0, 0, 1, 1, 0, 0. So this is 8-bit, or otherwise known as a byte. So what do these numbers mean? Well, these numbers mean 1, 2, 4, 8, 16, 32, 64, 128. So if we say, if all it is just you just count all these up where their representatives, where their bit representatives are ones. So what does this mean? It's 2, so this one 2 plus 16 plus 32. All right, so if we do this, 2 plus 16 plus 32 gets us 51. So technically this binary number is equals to 51. Now, if we take a look at this red channel, assuming that instead of 8 bits, you actually get only 4 bits, then technically, assuming all bits are set to 1, so that's 1, 2, 4, 8, which means you get a total of 16. Your value, your outcoming value is 16, which tells us that the red channel can be any value between 0 and 16, with 0 being black, 16 being fully red. That is what I am coming to the conclusion with. So this tells me that the Nintendo 3DS display is a 16-bit display. To be honest, I'm pretty sure somewhere out there this may have already been documented, but I haven't seen those documents. And if I'm correct, then hey, logic wins. My analytical skills somehow pulled through. So let's assume that this right here, so the display is actually a 16-bit display. This is like basically every color gets 16 gradients, 16 values, from 0 being black and 16 being white. As a matter of fact, this is actually incorrect, because if it starts with a 0, then the last value would be 15. If it starts with a 0. Yes, that's correct, because 1 plus 2, 3, 3 plus 4, 7, 7 plus 8, 15. So, yes, it's a 16-bit value, but it ranges from 0 to 15, 0 being one of those numbers. Anyways, ignore me on that one. So, what's happening here is that all of these bits, instead of being sent like 1, 1, 1, 1, 1, 1, 1, 1, 0, 0, 0, 1, instead of them being sent like that, you're actually sending all of the bits at once, which means you're sending, let's say 1, 1, 1, 1, 1, 1, 1, 1, 0, 0, 0, 0, 1. How fast is it? Well, that takes exactly 1 clock cycle. One clock cycle to refresh that 1 pixel. So you can see why parallel port programming or parallel display refreshing is quite preferable. It's because it's very fast. It's very fast. And you are able to refresh the screen just like that. I actually do have a couple of displays that have their drivers broken. So the drivers would have an HDMI input, a VGA input, a bunch of buttons, a controller on it, and then you can just connect the HDMI from your computer to that display, and it was just about like this big. The driver broke, but the LCD display is still fine, and I can actually see the ribbon cable, like this, with the solder pads. And I'm pretty sure that with a little bit of probing, I should be able to essentially find which pads belong to the, let's say, the red, green, blue channels, as well as the V-Sync, H-Sync, and clock signals. Okay, so let's talk about those for a second. As I said, the display of the 3DS is 800 by 240 pixels. So 800 by 240. Yowza. So 19 and 2000. Okay. This is how many pixels we have. Pixels. This is the entire pixel count of the screen. The entire pixel count of the entire screen. What does that mean for us? Well, for us, this is equivalent to 1 frame. The 3DS refreshes at 60 frames. So you time this 60, and that 115, 20,000. 115, 20,000. This is how many pixels we have to push through, read, and send to the over USB to our computer for reassembly every single second. This is how much data we have to work with. So every single one of these frames has red, green, blue channel, which are 4 bits byte size. So I'm just kind of breaking this whole logic apart right now, just so I can see if I can make sense of how I'm gonna really tackle this, because I'm going into this kind of blind. There was a little bit of preparation from the document that Hyas has sent me, and I can consult that, and there's already a lot of work done there for me, so that's kind of nice. I'm gonna do this. Okay, that is the total amount of data we gotta be pushing. That's a fuckload of data. So, not only that, we have 2 displays, but the bottom display is 320 by 240. So, there's a little bit less data going on there, but interestingly enough, if the bottom display does not have the same amount of pixels, then how does it go about refreshing the bottom display? and staying in sync. That's actually an interesting question. And this kind of ties into these values. So that's what we're going to take a look at now. So what are vsync and hsync and clock? Well, this right here is the clock. Right? This right here is the clock. Okay, so highest says it's 800 by 240 when it's in 3D mode. But then again, what do they just disable those pixels? I guess it would make sense. Although it's kind of weird. Why would you disable those pixels? Huh. I mean, in that case, it makes it a little bit easier, because then the difference is just 320 and 400 pixels per horizontal. You know, the pixels horizontally. But still, why? I don't know why they would disable them. I know that they can blank. The way they achieve the 3D effect is they blank half the pixels for one eye, half the pixels for another eye. And they have this polarized screen that essentially hides half of the pixels from the view. At least that's one of the ways to do it, and I'm fairly certain that's the technology they use to achieve the 3D effect. So even then, let's assume that it is 400 pixels in regular non-3D mode. These two numbers are still different. So the reason I'm wondering here is, how do we go about handling reading the data of the sync? See, if the height was different, then I would understand. But if the length is different, which is what these numbers are, then that is kind of weird. Okay, so what are these things are? Well, this is vertical sync and horizontal sync signals. We know what clock is. Clock is this one. Clock is this guy right here. That's the CLK. CLK. It's a legitimate data line, CLK. So what's happening here is that every time the clock signal goes up like this, it basically signals the LCD display, hey, we have a new set of color bits for you to read. Go and read them. Go and read them. So this is technically, this one clock signal is where the display receives red, green, and blue data for 1 pixel. Then the clock signal pulses again, and we get red, green, and blue data for the 2nd pixel. Then we get the 3rd pixel, 4th pixel, yada, yada, yada. It keeps going until it reaches the very end of the screen. When it reaches the very end of the screen, we get we essentially get a horizontal sync pulse. So let's say this was the entire, these are the clock signals for, let's call it 400 pixels. So that reaches from 0 to 400 pixels right here. When it reaches the end, horizontal sync fires a single pulse, which makes the display say, okay, we're gonna go to the next row, and we're going to start receiving our clock signals, and we're going to start receiving the pixel data for these clock signals as well. And that would be the horizontal sync. Although that might be the vertical sync. So, See, that might be... Okay, so that's actually where I was figuring out something might be wrong. We have VSync, we have HSync, vertical sync, and horizontal sync. So if we take a look at, let's see, vertical, horizontal sync, analog television, okay. Even though it's analog television, the idea is the same. Okay. All right, so line 1, vertical trace, horizontal trace. Okay, so horizontal trace, got it. I am correct. Horizontal sync tells it to go to the next line like this. So let's say these are our pixels. Horizontal sync tells us to go from here, from this point to this pixel right here. So if we end in this pixel and we receive the H sync, we receive that sync right here, then this is the point where we transition to the next line and we start from the beginning. Vertical sync, the VSync, happens when we actually reach the bottom of the display. And I mean, some people might be familiar with VSync as this feature on their display or graphics card, which basically helps with tearing. And that's exactly what's happening here. As soon as we go, you know, this, and we've reached the very last pixel, this is where the VSync is fired, and we are returning back to this pixel right here. And voila, we have a full picture. So that is the basic idea of how these displays work. So if we assume that the display, the 3DS display, is 400 pixels in non-3D mode, if it's 400 pixels in non-3D mode, then horizontal sync is going to come in every 400 clock cycles. Vertical sync will come at the very end. So it's going to go from the first row, second, third, fourth, blah, 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 blah. It's going to keep going until it reaches the end. Vertical sync gets triggered. We'll go back to the beginning right there. And I'm thinking vertical sync and horizontal sync might actually come into play. So vertical sync would come in at a rate of for 60 FPS. So once again, we're going to redo this math right here. This is assuming we're in 3D mode. So we're just going to call this 3D mode. And this is going to be 2D mode. Okay, so with 2D mode, 400 by 240. Okay, hey. 96000. Beautiful. So 96000 pixels. At 60 FPS, we have to basically multiply this by 60. Okay, 576. Pixels per second. That's how many pixels we're actually making the record of. So technically, the vertical sync should come every 576,0000 pixels. Again, I could be wrong, but this is where my logic is taking me. Or not pixels, well, technically pixels, but in this case, this would be CLK. Clock signals. I will verify these, or I'll do my best to verify these when I get my charger for the 3DS, when that comes into the mail, and when I will be able to plug this thing in, and I'm going to be able to take my scope and probe some points around and verify that information. Okay. So this is what I'm making out from this particular analysis. Yeah, when you have to push this many pixels, parallel port really does seem like the logical step. The main question is, will any of the controllers that I have be fast enough to read all of that data? So if we're reading 60 frames per second for that resolution, this is how many times we have to read the data from the display. Now what I'm thinking is that instead of pushing these things all at once, I'm thinking I can program the controller to read the bits and then wait for the VSync signal. Once it reads the VSync signal, this indicates that we're on the new frame of the screen animation, and at that point we can simply switch to using a new, just dump this data, dump all of the data for the current frame over USB, and just start working with the brand new data. Now, what do we have here? Highest has sent me something on Discord. The native top screen resolution of the 3DS is 800 by 240 in 3D. The way the 3DS works is that it essentially renders one screen for each eye. Okay, so there you go. And then overlays them on top of each other to create the illusion of real depth. Unless you want to record in 3D, just pick the 400 by 480 option. 400 by 480. Why 480? Unless you want to record in 3D, just pick the 400 by 480 option. 480 is this. Oh, per eye. What? Per eye? Okay, so I know that it's per eye. What I was thinking is, why is this number the same? And it's probably the same because your eyes are located on the horizontal line. So it would make sense that for the 3D effect, you just need to offset the image horizontally, which is probably why when you rotate a 3DS, 90 degrees, the 3D effect doesn't really work as well. It works because your eyes is the difference between the distance between your eyes that makes the 3D effect. So it would make sense that only the horizontal, right? Only the horizontal pixels would be different. Okay. So it says 240, 400 by 240. So unless you want to record in 3D, just pick 400 by 480 option. If you want to record in 3D, you can go to image 3D side by side. Oh, it may also crash your viewer program. Okay, so I guess this is for the third-party homebrew application that's supposed to dump the data that way. And that application apparently gives you the option of recording 3D if you have a way of reproducing that 3D locally on the machine, maybe with a 3D TV. Oh god. I totally forgot about the 3D TVs. Ooh. Wow, that was one hell of a gimmick. You don't have the new 3DS. No, this is You can switch to using the YouTube chat, by the way, instead of Discord. I'm just keeping an eye on it. For consumer services, okay, blah blah blah. CTR001 USA. Made in China. Yeah. 2011 Nintendo, 2010 CTRSUSZCO. Yeah, I'm pretty sure this is like the very first, the very first launch type or launch version. Yeah, seems like it. Okay. Right. So I might have to look into that as well. The second half, the answer to a question about how to record 3D using Cat's Kitty 3DS cards. Also, the 3D still works when viewing at a different angles with the new 3DS face tracking. Huh. Okay, well, with face tracking, they probably have like an algorithm that checks the accelerometer of the, or yeah, accelerometer basically of the 3DS, and they can adjust which pixels have to be blinked, so to speak, to get the 3D effect in whatever angles you use. But I'm pretty sure this is not one of them. I'm pretty sure this is the old one. I don't have the new 3DS. Okay. Is it the 3DS XL? Or is it like another version of the 3DS that they made that particular improvement on? The picture isn't about homebrew recording, it's physical hardware capturing card. Yeah, that's the Katsukity 3DS cards you were talking about. It's a 3DS with a nipple. Oh man, that brings me such joy. Okay. So, I modded my 3DS. Ooh, what with? What did you use to mod it? So, in the meantime, here are my thoughts. All of these bits for the display data go into the 3DS simultaneously using the parallel port. So realistically, the total amount, this is the total amount of pixels, if I am correct. 400 by 240. Do you play Luigi's Mansion on both screens when you play the game? Because I'm probably gonna have to dump both screens. Homebrew and Steel Hacks. Oh, cool. What's Steel Hacks? What is that? Let's see. 3DS Steel Hacks. Homebrew launcher, Steel Hacks. Okay, so so you installed custom hardware, custom firmware onto the, well, maybe not custom firmware, but it's an exploit. It basically runs off of a 3DS to give you homebrew capabilities, and I'm guessing you're just using an application that can dump the data. So yes, you can do that, but I'm more interested in trying to make this hardware-wise, just to see if I can make the hardware of it. Now, here's my general plan. Here's my general plan for the hardware of this particular application. If we take a look at the 3DS LCD, what I'm doing right now is I'm researching into the way the 3DS hardware works, so that I can make basically like an interpreter that sits in between all of these pins and the output LCD, and reads the data off of the LCD without using up any of the 3DS cycles. So without using up any processing power, no homebrew applications, no custom firmware, just reading the raw data of the LCD's display and then dumping it onto the hardware. Now, Hyas, is this the, what's the Kit Kat Kitty something thing? Because I don't know what this is. It's blue. That's what I know. That's all I know. Would be great if I could get a translation of this. So yeah, my idea here is to insert, instead of this, insert my own controller, connect them to these pins, and see if I can read the data using that instead of any custom firmware, so to speak. Are you going to be using a 3DS just for the screen or just the screen? No, the 3DS. Like, what I'm saying is I want to take the video footage off of the 3DS and build something like a video capture card for it as an experiment. Instead of using the homebrew way where it's just software and you just connect the USB, I want to see if I can do it in hardware. Right? So that's basically what I'm doing here. I'm just kind of analyzing all of this data to see, just to make sense of all these things. So what I'm making out here, if I take a look at their okay, right. So if I take a look at their page, we have all of their pins for all the displays: red, 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 blue, 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 green, and then we have another pair of red, green, blue pins. Which 3DS I'm using? To be honest, if I knew, I would be able to tell you. It says this is the CTR-001 USA. Let me see if I can. Let's see if I can do this. Okay. Can you see that? No, you can't. Yeah, you can't see shit like that. Okay. Here's what I'm gonna do. Gonna snag a photo. Oh man, HLVR Alex has been announced, so I'm like, ooh, interesting. Yeah, it's said on the title, or it said on the listing that this was like a launch console. So I'm pretty sure it's like the first one, the first one. The firstest there is, essentially. So hey, I mean, it's an experiment. If anything, I mean, these soldering to these pads is pretty non-intrusive, at least by my standards. So I should be able to just, if anything, just desolder them and use them just the 3DS by itself. Okay. So we have clock, we have vertical sync, we have horizontal sync. What I want to try to do, however, the soldering to these pins is only temporary for the purpose of just me experimenting with the stuff and just, you know, seeing if it's just for the feasibility of it. See if I can even take the information off of it. What I really want to do, if this works out, if I can read the information from it successfully, I can essentially read the data from this port right here, if that is the LCD port. The 3DS has a few of them. So instead of soldering the pins to here, basically what I want to do is make like a intermediate ribbon cable connection that connects to one of these, you know, ribbon cable snap holders, and the actual LCD ribbon cable will just connect somewhere over here. So just to visualize it, if we take, for example, that ribbon cable, let's assume that that ribbon cable is the LCD display. So to visualize, what I want to see about doing is I want to have a little intermediate device. Let me just make it like in red. So it would be sitting, connecting here with all of its pins, and maybe a bus will be sticking out from the 3DS. Just like that. Then there would be a secondary header, and to that secondary header is where you would connect the native 3DS LCD display screen. Just like that. So snap this, snap that, and this is kind of, it's basically going to be duplicating our signal like this. Direct pass-through to the LCD of the screen, and then we're going to get duplicates going over here. So both the 3DS display and the screen of the 3DS and the controller will be able to get access to that information without even soldering anything to the board. At least this is what I want to see about doing. We'll see if it works out or not. So if we take a look at the 3DS LCD display, for example, this guy, open a new tab. Okay, so that right there, that ribbon cable, that doesn't even look like there's a lot of pins there either. Now those, I'm pretty sure, are the digitizer pins. So this is for the touch screen. Or no. That, if this is the top display, then this would be the little overlay that allows you to basically kind of blank the halves of the display to make the 3D effect. Okay. That, oof, ouch. That's ouch. That is what I'm looking to do here. I mean, this pretty much outlines most of what I want to do. One last thing that I really need to figure out is the arrangement of this data. So if I take a look here, TP stands for test point. This is the name of the pin. Test pinouts for the front of the board. This page documents the procedure of capturing the video signal of the upper and lower screens. This is the main clue that I have, that these are actually, this is the data for both displays. Signals for upper and lower screens of the 3DS. So there's got to be a reason why they're bundled like this. Red 0, 1, 2, 3. Oh! This has been organized for us. This little table right here. Hold on. This is why I thought, what the hell? I made sense of this before. Why can I not understand this? This table here from the journal has actually been reorganized for our viewing right here. Okay. R0, 1, 2, 3, 4, 5, 6, 7. All right. Green, 0, 1, 2, 3, 4, 5, 6, 7. And blue, 0, 1, 2, 3, 4, 5, 6, 7. So these are probably just the names of the pins, and then we have the clock, vertical sync, and horizontal sync. To be honest, yeah, the wiki says this is for both displays, so yeah, each display has 4 bits of data, which means that each display it has a total of 16-bit depth in color. Okay, really cool. So it says test point above 180, test point below 172. That's what those mean. So test point above 180. So if we go over here, where's 180? TP stands for test point, right? That's what they said. This table taken from the picture above shown which TP test point to test the bit of the corresponding color. Test point above 180. So, oh, here we go. TP 180. They're on the board. That's not the red labels. It's these guys. Okay. Yeah, most of the homework has been done for me. All that's left to do is to really pick a controller that is going to be fast enough to get the job done. So, I mean, I have some stuff sitting on my desk that that I'm playing around with. So let's take a look at some of this stuff. Boop. Okay. First of all, this guy's just kind of sitting on my desk, but it's kind of irrelevant. This is an Atmega AT2560. It's a 16 megahertz processor. It's not going to be fast enough to read all this data. Nowhere near, for sure. But I have yet to take it down to the shop and put it in a box, so that's why it's sitting here. The next one, the one that I'm going to be doing the tests with, is this fucker right here. This is an STM32F407Z. This guy is a one heck of a beast of a controller. So first of all, it has an SD card. It has an SD card, which means that should anything happen, I should be able to at least read the information from the 3DS and dump it on an SD card. If I can't figure out how to send the data reliably over USB. But it does have a USB connection, and I have set up this thing to connect as a, CDC device, which means that I can send serial data with the frames, frame information to the computer using serial. I have yet to test whether or not it's going to work. As I said, didn't include the power supply, so I can't do it now. Gotta wait for that shit. And I also have to wait for the screwdriver to arrive, so yeah. Just gonna have to wait. So, this particular guy, as I said, the Atmega 2560 runs at 16 megahertz, not fast enough to get the job done. However, STM32F407Z, this controller runs at a whopping. Oh, come on. Sure, accept cookies. Whatever. Oh, God's sakes. Do you really have to reload the page if I accept the cookies? Okay, so this guy runs at a... Jeez. What are we running at? Where's the speed? 168 megahertz. So, 16 megahertz, 168 megahertz. That's the difference. So, we're gonna look at... And, of course, it would help if you can see my screen, Right, so STM32F407Z runs at 168 megahertz. It's got 192 kilobytes of RAM. 192K of RAM. Okay, let's take a look at that. Let's actually do some math. So, our limit with this particular board, RAM is going to be important because before I can dump the data onto the USB, I want to see if I can store it on the device, on the controller first, before dumping it onto the USB. Because once again, this is where we're talking about dump the packet of data that has all the pixel data, all the bytes for the image for one frame, versus dumping every single cycle, dumping the 12 bits every single cycle, which is, this many times per second. Right, so let's take a look at the math here. So we have so 5,760,000 pixels in total. That's when we have 400 by 240. That's correct, right? Let me double check this. I don't trust myself. 400 times 240. Oh, right. Yeah. That's correct. This is one frame. This is one frame. So let's work with a single frame. That's the thing. I'm gonna be sending single frames, not 60 frames at a time. I'm gonna be sending single frames. So this may look a little bit more promising. So we have 96,000. So let's go over here. 96,000. That's how many pixels. Each one has red, green, blue, each one of these has 4 bits, which makes this a total of 12 bits. 12 bits per 1 pixel, which means that it's this times 12 bits. That is how much memory. This is how many bits we need. So 115. Interesting. That number seems awfully similar to something I got earlier. Okay, maybe it's just me hallucinating. Right. Yeah, come on. 115, 2000. So 115, 2000 bits. When you send data to the USB, you have to send it in 8-byte chunks. So you have to set 8-bit chunks, which is, like 1 byte has to be an 8-bit word, so to speak. So we're going to be combining some stuff. So if we divide this by 8, this is how many bytes will be in one single frame. Bytes. So 144. What was it? 144. Yeah, come on. Oh, am I No, I'm doing something wrong here. I had 2 calculators out. Let's do this again. I goofed up again. 96000. That's how many pixels in a single frame times 12 bits divided by 8. That's how many bytes. Okay, that is actually that is actually correct. Let me just do one last check, because if two out of the 3 is going to be correct, then we know we've hit the jackpot. All right, this is how many pixels. Each pixel has 12 bits of data, and then we're gonna divide it by 8. So okay, 144, 0, 0, 0. So this is how many bytes. Now, that's bytes. We are looking at byte to kilobyte. So kilobyte, I think, is 1,000 bytes. So if we say we need to supply this many bytes, 144 kilobytes. 144 kilobytes of data per one single frame. 144K. Which puts into perspective what it is that we need to do, because the STM32F407 has 192 kilobytes of data. 192. We fit. It's fitting. It fits. Yes. Okay. The math pans out. So this is STM32. Excuse me. What? Saying one thing, writing another. 32F407Z. That's the controller we're going to be testing this with. Okay, fine. Now there is another controller that I'm receiving at some point soon, since I have invested some interest into this to look if I can find any other controllers. We're looking at an ESP32. ESP32 is one of these controllers, $8, not bad. Let's take a look. So ESP32, let's look into the specs. Okay, here we go. ESP32, different LT devices, thank you very much. High level in, come on, give me technical support. No, I need technical data sheet. ESP32. Okay, So here we have 4 chips. Alright, CPU and memory, functions and descriptions, features, solutions. Okay, these are communication features. We don't want that. We want regular specs. Bluetooth features. Oh yeah, this thing has Bluetooth and Wi-Fi. It's kind of cool. MCU, advanced features. Okay, it's a 32-bit controller. 32-bit controller. 520 kilobytes of RAM. Good. And then let's take a look at the clocks. This thing runs at... this thing should be running at 260 megahertz from what I have seen. Clocks and timers. Well, these clocks and timers, they don't necessarily mean the full speed of the controller. That's just some of the clocks that drive the controller to reach whatever speeds it is working at. I think I might have missed the number. Complete solution. Huh. And here we have Gpio settings. CPU. Aha! Here we go. 240 megahertz. And these we have 160 megahertz for this version and that version. Okay, and it's a 32-bit processor. Does it have USB? I don't think it has USB. USB 32. Low cost, low power system on a cheap microcontroller. It does have USB. Yes. Right over there. So, we should be able to... I mean, it's coming. I ordered like 3 of these things. I kind of went overboard because there's a bunch of different versions. So I wanted to make sure that I get the right one with at least one of those purchases. Lots of RAM to work with. That's kind of interesting. Another thing that these guys have, which is kind of besides the point, is one of these chips... I think the latest one has touch sensitivity, which means you can actually make very cheap touch buttons when you can, instead of like clicking on the button, it's just like touching a metal pad and it does whatever you want it to do. So that's kind of interesting. Speaking of which, yeah, I did say that the STM32 has a USB, not the USB, it does have the USB, it also has the SD card reader, so possibly could make a portable capture device, portable capture card, where it basically just you plug it into a system and maybe it captures the video on the go. Like imagine this, if you're working with a 3DS and you want to go to a park and play, I don't know, like it's Pokemon, I guess, something. What can you play on the 3DS in outside that you can't really fully enjoy at home? I don't know. You probably know more than me, but pocket screen capture on the go. Like doing a let's play of a 3DS game in a coffee shop, for example. Imagine that. Right? So, I mean, that would be kind of spoiling myself, but hey, if anything, this could be maybe like for those people who want to do a spontaneous let's play. Maybe I'm meeting up with Tim and we'll want to do a Retroactive Gamers episode. It's like, hey, let's do an episode right now. We'll just pull up like a portable... We'll pull a portable field recorder that I would just so happen to maybe randomly have in my pocket as if I wasn't planning on recording anything. And yeah, just get the vocals recorded and get like a spontaneous let's play. To be honest, I can totally see that happening. Because sometimes we kind of meet up for just randomly meet up to play something. And on a bunch of occasions, I've actually found myself thinking, man, would it not be great if we could like record this? We'd be playing a game and it'd be like, oh, I really wish I recorded that. And this could be a possible solution to that. So yes, these are the controllers that I have in my mind when I'm thinking for a solution to this project. So yeah, we got it. 192K RAM. I think I've pretty much talked about everything in here. This would only do video for now. I would have to implement audio, which to be honest should not be anywhere near as challenging of a problem as video capture. But, you know, one step at a time. One little baby step at a time. Okay. Let's see, did I miss anything? And or am I going to make sense of it all tomorrow when I look at these shenanigans? Let's do a little mock-up demonstration. So let's say this is the 3DS connector. We'll get the pins going in the back. Kind of going like this. So the little cable that I told you about earlier that I want to see about making goes inside of this connector like this, and it will have a little break right here, which will allow me to get the data off of it. And to be honest, that break, that's just like an off the top of my head, considering that if this right here, this other end, is supposed to contain essentially another one of these. So it would very quite literally look like this. Right? And this is where you would plug in your 3DS LCD port for the display, and your LCD output would essentially go right there, and it's just, you know, that's where that's going to go. So technically, if I look at it this way, if we have a pass-through for all of these wires, however many pins we're going to have there should be pretty much all of these pins. All of these pins right here should have their own trace. Every single one of these pins should have their own trace here. Which, if we start with 1, then the last number is 27. So a total of 27 traces in here. 27 being right there, the H-sync. So the problem here is that I probably won't be able to kind of move them like that, because you see the traces are going to overlap. So chances are I'm going to have some pads here. So if I take a different color, I'm going to have some like pads right here on this little ribbon display cable, ribbon cable, and I'll simply have to solder like a secondary ribbon cable that goes up like this. That's one of the possible solutions. Or wait a minute, what am I doing? Of course I can have a side view like this. Of course I can have a side output. All I have to do is, let's say this is the ribbon cable. That's supposed to be the side output to the card. The top one is going to have our pass-through. However, on the other side, we're going to have an output basically mirroring but going that way. This is all on the other side. So it's a double-sided PCB essentially. Okay, so that actually solves that problem. So we can get away with making just a single ribbon cable. That should be more than fine. And to be honest, this total space right here between this connector and this one can be minimized. That should take very, very little amount of space on the board. Now, when it comes to these ribbon cables, like that is like a really advanced thing that I'm trying to go for. As you've seen, a lot of people just say, yeah, just solder your pins, solder wires to this thing. But for me, it's just, I just want to see if I can make it happen. If not, then whatever. I'm sure I will have learned something along the way. Let's see. So here we actually have the two boards. And yeah, I do have a second 3DS coming that's broken, which I can crack open without any fear of breaking it. What am I gonna break it more? It would suck if it worked and I would break it, but yeah, this should be just fine. Okay, so if we take a look at I think that right there looks like a display ribbon cable as well. If we take a look at these ribbon cables can be ordered and made and designed. And the company that does them, I think, is PCB Way Flexible Cables. There we go. Okay, so this is what we're looking at. These like rigid flex or flex cables. Now, do they have a catalog that I can actually take a look at? I've done orders with this company before. For now, I'm using JLC PCB, but they don't do flex cables. So I'm going to be doing this. They also do assembly, which is really cool. Simply just make a design that works and send it for assembly and receive a ready product, which is really, really, really cool. I'm not really a fan of assembling teeny tiny little bits and parts, especially when they're surface mount components, which are freaking tiny, right? You can do it, but okay. So we have the product center. We're looking for flex PCBs, rigid flex. There we go. Although rigid flex means there's a rigid part and a flexible part, like this. So I think I am actually looking for flexible PCBs. There we go. That is exactly what I need. Precisely what I need. Yeah, so imagine something like this. This end goes into the 3DS. I mean, over-exaggerating, but this end goes into the LCD, and this is the output. Grossly over-exaggerating it, but that's the basic idea. And that's it. I think I pretty much have that system. So realistically, this would make quote-unquote modding your 3DS somewhat easy. You just pop open the lid, lift the flex cable, the ribbon cable, insert the adapter, close that up. That's it. But then again, I could always try. What was that that other capture card called? It was the Katsukiri 3DS. Was it me, or was that particular capture card? Oh, this is so slow. Was it me, or was that particular capture card actually replaced the bottom of the 3DS? Yeah, like this. There was a lid. Okay. Now what do we have here? New 3DS XL capture card. Okay, so we just had the 4 ports right there, so they kind of drilled out a little hole to make the port come out. There was also this guy right here. Katsukiri added a chunk. I mean, this, to be honest, makes a lot of sense. if you don't want people to deal with loose ribbon cables, then it would make sense for you to design your own board and put it into your enclosure and just have it as a separate attachment. Because one way or another, something's going to be ugly. Either there's going to be an extra little board, a little thickening with the additional hardware. Hey, look at this. They got a ribbon cable going in there as well. That's really cool. Which I'm pretty sure they actually were trying to do the same thing that I'm doing here. Well, they probably achieved it since this is a real product. Hey, we have HDMI outputs by the looks of it. That's kind of cool. I bet. So you're saying this is no longer available? Is that it? Saying this is no longer available, and that's why it's like skyrocketing. A lot of time the IR sensor is removed. Oh, so you remove the IR sensor and they use its place. That's interesting. And you remove its place. You put maybe like a USB output. Interesting. How many versions of the 3DS are there when you say accounting for the different designs? Because if there's a whole bunch of different 3DSs, hey, look at that. Man creates machine to hunt, capture, clone shiny Pokemons. Oh, that is hilarious. That is awesome. Man creates machine. Florida man arrested again. Interesting stuff. Oh, somebody using a camera and a webcam. Oh, since cat's a kitty, card never or what? Card never something something. Interesting. This is really interesting. They just have a bunch of ports out. I assume this is for the USB connection of a sort. Or this may be just a pass through for the data. And then they have another dongle on the outside, like right there. We have a nice USB connection. Really cool stuff, man. People are doing a lot of innovative things. 3DS XL capture card. Yeah, all of this stuff seems to be pretty much doing the same. All of this is out of... Really? $354. Not dollars. These are euros, I think. What is this in Canadian rupees? Wowza. CAD. Jesus. Are you kidding me? Oh my lord, that is... Oof. Ouch. Man, Nintendo users are not having a good day. How many different 3DSs are there? 3DS revisions. It's a business. Could be. Could be if I get it to run and, you know, be okay. I mean, if you get the ability to capture the screen, would you mind an extra layer, like an extra thickness, extra back for your 3DS? It is interesting. I'm seeing a lot of people, well, I'm seeing quite a few products that implement... I posted them in the comments. You posted them in the comments. Wait, what? Oh, comments, I'm assuming the Discord? Or not? Yeah, I'm not seeing which comments. Read above. Post them in the comments. I don't see... You're gonna have to do that again. Live stream chat. Oh, I can't, like, is this Twitch live stream chat? You're gonna have to do it again. A lot of the time the IR sensor thing is removed. Katsukitty added a chunk. Pokemon Sword. And shield was okay. Yeah, you're gonna have to post it again, man. Let me take a look at the revisions. Release date. Games, comparisons, reception. Video services. Hardware. Console contains 2 separate screens. A 15:9. Ooh. Auto stereoscopic LCD display. 400 by 240 pixels. On the original 3DS, the screen measures. 3DS screen measures. Interesting. Dude, if it's the... just post it again. I can't see shit, man. Standard NFC reader. Oh, well, here's something. There's the 3DS XL, and the new 3DS. This has added the nipple stick. The nipple stick was was built in? Oh, that thing right there. I see it. And as a matter of fact, this is where we got it. So Nintendo 2DS, 3DS, 3DS XL. So there aren't really a lot of revisions. 3DS XL. Yeah, that's kind of like a lackluster edition. The little nipple. 3DS, 3DS XL, Nintendo 2DS. The new Nintendo 3DS, new Nintendo 3DS XL. And what is this? New Nintendo 2DS XL. Okay, so we got 1, 2, 3, 4, 5, 6 different Nintendo 3DS models. Well, people say they are more or less similar. Let's see. Okay, so if you're designing something universal, then you probably want to make sure that you put in some sort of settings that allow you to change how big the screen you're actually capturing. So that is a big ass screen on the bottom. Holy cow. That's awesome. Now, if that's the case, how big is the screen on this one? 5 revisions. Okay. How big is the screen on the 3DS? 3DS XLs. XL. Okay. CPU dual core ARM 11 processor, 268 megahertz. So yeah, they have more than enough speed to refresh both screens at the same time. But then again, they are doing parallel programming. Oh, parallel, pushing the information to parallel port. Graphics, 133 megahertz. That could be the speed of the processor, not the refresh rate. Got the mass, medium. Okay, let's take a look at the hardware. Yeah, I see it. There's 5 revisions. Oof. I mean, hey, that doesn't look too bad. Doesn't this bottom part leave indents on the top screen? People complain about that. Like, they leave scratches on the top screen. Doesn't leave indents. Well, okay. Yeah, well. So it does. I'm not seeing the screen information here. For the big one. Let's try IQ? Camera sensors, maximum resolution. Don't care about that. All of the resolutions are the same with each revision. Well, I mean the 3DS XL. I want to see what the 3DS XL resolution is. So let's do Nintendo 3DS XL resolution. So I want to do the math. 800 by 240? What? However, in the 3DS and 3DS XL, the top screens has double this max resolution. Is the height? Is the height of the screens the same? Okay, so here's the thing. It's the same resolution, just a bigger screen. The problem is that if it's a bigger screen, if it's the same amount of pixels, just a bigger screen, then I guess that makes sense. And I guess that would make sense, because then nobody has to redo their games for just to update them to 3DS, is what I'm thinking. Okay. So realistically on a 3DS, the screens use all the same effective resolution. 400 by 240 pixels on the top screen, 320 by 240 in the bottom. However, the 3DS in the 3DS and 3DS XL, top screen has doubled this maximum resolution to 800 by 240 in order to do 3D. So what? We just get bigger pixels? That's kind of a weird way to go about it. Because here's the thing, there's the virtual resolution, and there's the physical resolution, which is how many pixels we have on a display. And I just want to be really sure that they are both the same. Okay. Screens. Same size screens. 2DS and 3DS have the same size screens. You get the display up to the slightly smaller 3.02 inch screen below. The 2DS screens are actually part of the single flat screen that's split in two by the plastic surrounding the console. Okay. That makes sense. Interesting. Well, that's a 2DS. The Nintendo 3DS XL. Wait. The 3DS screens are actually part of the single flat screen. So does that mean if you crack open a 3DS, it's just going to be like a long screen? That is interesting. I am Canadian, yes. Penny for scale. Highest is like, oh wait, you're Canadian. Is the dimension of the console itself the same? No. If the D-pad is the same size, there's no way the 3DS's dimensions are the same. There's no way these screens are the same. I'd have to get a 3DS XL now for comparison. Okay. Here's what I want. What I really want. The Nintendo 3DS XL and new 3DS XL have a much larger screens. They're 4.8 inches, just like the previous DSi XL, though you don't get a real increase in image quality, just image size. Okay, so this should pretty much tell us that it's just bigger pixels, not more detail in the screen. The screens all use the same effective resolution, 400 by 240 for the top screen, 320 by 240 for the bottom one. However, in the 3DS and 3DS XL, top screens have double its maximum resolution, to 800 by 240, which is kind of useless for us unless we want to be able to record 3D, which, you know, it's maybe next time. For now, it's just baby steps. The 3DS XL has a ton of larger screens than the original. Okay, so if this resolution is what we have to work with, then I think this should be fairly straightforward. And I'll look into maybe... Oh, shit. Right. Interesting. Oh. Fascinating. My brother has a Switch, so, I mean, I can kind of look at that for comparison. Huh. Man, I kind of want to get a... What is a 3DS XL? Hi, so you might want to send horizontal images like a civilized human being. 3DS XL. What does a 3DS XL actually go for? 90 bucks, 100 bucks, refurbished with Pokemon Y. Interesting. 167, like that is a good deal. 20 bucks shipping. 90 bucks Canadian. Manufacturer refurbished. This should be a good deal. 3DS XL red. 49. Oof. Wow, a lot of bids. A lot of bids. Everyone wants to get that cheap stuff. Can we just do buy now? I don't look at this. 50 bucks. Broken Wi-Fi receiver. Oh, man. Do we care about the Wi-Fi receiver? I don't think we care about the Wi-Fi receiver. If anything, we can always replace the Wi-Fi receiver. Repair it. 60 bucks for 3DS. 3DS XL, I should say. It's not bad, actually. Not bad at all. Limited edition Majora's Mask with what looks like a capture card. Refurbished, that's the sponsored listing we saw earlier. I want to play Scare-Scraper with you when its Wi-Fi is important. Well, okay. If I want to play Scare-Scraper with you, then Wi-Fi is important. Yes, we also need to get you into Canada. So, you know, get your butt to Niagara Falls and start swimming. Ooh. 3DS black, 25 shipping, trending. Yeah, that's a good deal. 170, 200, 171. Okay, so let's see. This is the refurbished one. This is the one with the busted Wi-Fi. At least the power adapter is included. Okay, so if we take a look at 3DS XL Wi-Fi replacement. Okay, Wi-Fi cable antenna, 3DS XL wireless aerial fits for Nintendo, 10 bucks. Okay, I mean that seems like a very reasonable fix. 4 bucks, 3 bucks. Yeah. Oh man, this is more than reasonable. Screwdriver, wireless Wi-Fi module, circuit board for Nintendo 3DS XL. Man, 13 bucks? Okay. Let me copy this. Let me see if I can do this. Hey, and if I actually get it to run, then it will be an extra little video content for the channel. Repairing the Wi-Fi adapter. Just go ahead. Just buy it now. If it works. I don't know if I have enough. No, thank you. Don't want the warranty. That is okay. So that would be three 3DS consoles that I would have. The 3DS, 3DS XL and another broken 3DS. Ooh, okay. Well, it is what it is. And okay, that's it. I ordered it. So realistically, all that I need is one of these guys. 3DS XL wireless aerial fits for Nintendo. 3DS. For 3DS, for 3DS LL, XL. Well, this is interesting. Can we pick one? This is just for the antenna. And to be honest, I don't even know what is it that's actually broken on that one. If it's just the disconnected antenna and they didn't want to crack it open because they were afraid they were going to bust it up. If it's just a teeny tiny disconnected cable, which is that little metal piece right there, as I'm pointing to the screen with my finger, this metal piece at the very end of the wire, then that's a very easy fix. This is just the antenna. Now, if we take a look, if it's this guy, which is the actual circuit, the module, comes with screwdrivers. That's kind of cool. Oh yeah, and I still have to wait for my screwdrivers to come in, so that's another thing I have to wait for. Okay, well, see, either I can order it now, and if that is the defect, then that's what I replace, or I make a 2-video parter where I crack it open, I see what's wrong with it. If I can figure out what's wrong with it, then I order, and a part 2 is when I actually fix it. Okay, all right. So that is it for today. I have my analysis, my game plan, and we will see you guys in the next video, where I'm going to be working on cracking this thing open as soon as the power adapter comes in, as soon as the screwdrivers come in, and we'll get it up and running. Okay? All right. That is it for today. Thanks everybody for watching. We'll see you next time.